And as Heather mentioned, we're going to be talking about wheat nitrogen management both fall and spring this afternoon. All right, before we do that though, let's talk about corn and residual nitrogen and the impact that residual nitrogen can have on the performance of wheat. What you see is a slide that's showing average corn yield over the last 30 years or so for the state of Maryland. And as you can see, we have a lot of peaks and a lot of valleys. The valleys are those years when the performance of corn was well below average. The line that you see traveling through that, all those points, is the trend line. So over the last 30 years, we have seen an improvement of yield, but there's also been a lot of variability in that yield, which is based upon the precipitation that we get in any particular season. Because of this variability in precipitation, it's very difficult to optimize your corn nitrogen rate, primarily because of the last opportunity you have to supply nitrogen to the crop. Because of that, we see variable amounts of post-harvest residual nitrogen remaining. Now, in regards to wheat, this residual nitrogen or nitrate in previous years had generally not been measured. So this research was focused upon utilizing that residual nitrogen. One of the things you're going to notice as we proceed through this today is that the green pointer will stay on the screen all the time rather than my turning it on and off. So where you see it when it first comes up on the screen, don't pay that much attention to it. If I want to point something out to you, I will move the pointer to where I would like it. Now we know that when we have residual nitrogen, if we plant a cover crop, and in this case we're going to use wheat as the example, and these are actually a couple slides from some cover crop work that I did a few years ago. It was looking at various planting techniques. What I want you to focus on though is this circle right here. That was wheat planted. For the blue bars, it was planted right at the end of September, or for all intents and purposes, October 1. The red bars that you see next to each of the blue bars indicates a planting date that was near the end of October. What we're seeing is the amount of nitrogen taken up by the wheat planted on that particular date and measured the following spring when we actually sampled our cover crop biomass and then measured the nitrogen uptake that occurred. Now we have two different years there. They're very diverse. The first year, 2007, was a drought year. The field was fertilized for 140 bushel crop, which means there was 140 pounds of nitrogen applied, and the yield was actually 106 bushel. Nitrogen consumption for the early planted wheat that year was nearly 55 pounds to the acre by the following spring. The second year was a good corn year. Again, 140 pounds of nitrogen was used. The yield was 134 bushels, so most of the nitrogen was consumed. And you can see that in the performance of the wheat inside this circle right here. Early planted wheat consumed roughly 18 pounds by the following spring. The later planted wheat consumed about 10 pounds by the following spring. All right, because of that performance that cereal can have in consuming nitrogen, residual nitrogen we have, Maryland established a cover crop program starting back in 2003. And as you can see with this slide here, that program has been growing steadily ever since. And in fact, this last year, there was 607,000 acres approved for the program. There was actually 429,000 acres planted, and of that, 43,500 acres are in the commodity cover crop program. Now, this commodity cover crop program, which was established in 2006, pays farmers $25 an acre. There are some restrictions. Number one, they cannot use any fall nitrogen. They can't put any spring nitrogen on until March 1, which is the target date for the state. although the last couple of years the state has moved that target date to February 15th because of the milder winters that we've had. There's some questions surrounding this program when it was first established, and that's because many farmers were in the habit of using fall nitrogen, and if they didn't use fall nitrogen, they were wondering how well would their wheat perform without it in the fall, or would they lose money by not using fall nitrogen? And is there any way to know which fields would be the most responsive? Is there some sort of a test that can be used to identify those particular fields? As you all are probably aware, effective last October, there was a new regulation regarding the use of nitrogen in the fall for small grains. And that regulation states that starter fertilizer nitrogen is not allowed unless a soil nitrate test is done to determine the sufficiency or the deficiency of the soil. Now, we have this regulation. Is there science that supports this regulation? And that's what I'm going to be talking about during the first portion of this webinar this afternoon. And it's actually going to be the research that was conducted by my PhD student, Dr. Patrick Forrestal. He did the work on this fall nitrogen evaluation and the development of the fall nitrate test, completed his work in 2011 and has graduated and since moved on. Let's start by looking at wheat growth and nitrogen uptake. This chart that you're seeing on the right side of the slide indicates nitrogen uptake on the y-axis based upon days from emergence of the crop on the x-axis. And as you can see, it's a curve type response. Very little nitrogen taken up really during the first almost 150 days following emergence. And then once we get into green up in the spring and move on towards the boot stage and heading, you get a rapid consumption of nitrogen. Now we're using October 10th as our emergence date here. The old recommendation for fall fertilizer nitrogen was there was none required if you have an adequate amount of residual N present, and if you didn't have an adequate amount, you could use 30 pounds of nitrogen. However, there was no description of what adequate meant. There was no description of what low meant. And of course then the goal is, if you're not using any fall nitrogen, to get that spring nitrogen supplied at a point in time that you start getting rapid growth in the spring. Split applications are recommended. The first application goes out at green up. I have a couple of question marks there because what exactly is green up? The state defines green up, as you can see where this pointer is right there, as March 1, or that's how they've described it in the last few years. And the other half of the spring nitrogen is put out at joining, or not necessarily the other half, but the remaining amount of spring nitrogen that's going used goes out at joining. All right, so what approach was taken to addressing this fall nitrogen question? Well, we started again with corn. We established corn plots that got 4 different rates of nitrogen, and you can see them in this picture here. We had a 0 nitrogen treatment, 120 pounds, 180 pounds, and 240 pounds. We then harvested the corn. Immediately after completing harvest, we sampled within each of those fertilizer treatments the soil to a 2-foot depth and measured residual nitrogen. We then planted wheat into each of those fertilizer treatments, corn fertilizer treatments, and we put out rates of nitrogen of 0, 15, 30, and depending upon the location, the high rate was either 45 or 60 pounds to the acre in the fall, prior to the planting of the wheat. The nitrogen management in the spring was uniform. We put our first split out, and that split was 50 pounds on March 1, or as soon as we possibly could following that date, and the second split went out when joining started. Over the 5 years of this research, we did have a total of 21 site years. We had a variety of soil types, primarily silt loams and sandy loam soils. So to answer the question, does wheat respond to starter nitrogen? And I think you can see the answer there, that yes, it does. And in fact, we saw our best response occurring with the use of 30 pounds of nitrogen in the fall. However, that yield response was modest. It averaged about 3.5 bushel to the acre. I also want to point out that the sites here that you're seeing the nitrogen response were 16 of the 21 sites where we had less than 15 parts per million residual nitrate in the fall. We did not use the sites where we had adequate amounts of nitrogen because we did not see response at those sites. All right, let's take a look at that response to nitrogen in a little different fashion. What you're seeing here is every comparison that we had over that 5-year period, every comparison we had between the use of 30 pounds of fall nitrogen versus no fall nitrogen, at a total of 278 of those. In the scatter plot, each of those dots indicates what that response was. Now, to orient you a little bit with this chart, this axis here is describing the amount of residual soil nitrate that we had at the 6-inch depth. That's what the amount was at the 6-inch depth. So if you're here at this dot right there, there was about 32 parts per million at the 6-inch depth. This axis here, and this is the zero line, if it's above the line, there was a positive yield response with the use of 30 pounds of N. If you're below the line, there was a yield loss with the use of fall fertilizer. The red line that goes through there is a very loose description of the trend line. And what you're seeing is as residual soil nitrate increases, the yield response has a tendency to approach zero. All right, now there's a cost associated with the application of fall nitrogen, and that's what this blue line is indicating. It's that break-even price for covering the cost of the 30 pounds of nitrogen and the application cost. And on average, during that period of time, we were at about 3.5 or 4 bushel was required to break even. This red line describes Virginia Tech's current recommendation, and they recommend if you have greater than or equal to 30 parts per million residual soil nitrate, you do not need any fall nitrogen. If you're less than that, then they recommend the use of some nitrogen in the fall. However, we were concerned about this area right here where we had quite a few examples of response that was below what we called the break-even line. And so we used 10 parts per million as the point where we were seeing the most profitability. This area here, it was above the blue line, it was profitable. These comparisons were above the blue line and to the left of the 10 parts per million. And that made the probability of a profitable return the best. We're going to take a little bit different look at this response in this next table that I have. Now what you're seeing here is a description of those 278 comparisons that we had. We divided them into the categories that we saw, 0 to 5 parts per million soil nitrate, all the way up to greater than 20 parts per million. See that the majority of the comparisons that we had fell into this range right here where we had 10 parts per million or less residual nitrate in the fall. Now, this next line is that delta yield line, or the number of times that we had a positive response to 30 pounds of nitrogen in the fall. And you can see that about 2/3 of the time, if we had soil nitrate less than 15 parts per million, we got a positive response. But again, that's not the whole answer to the question, because you need to do an economic assessment on that, and that's what you're seeing in this yellow box is the economic assessments with a couple of bookends that we created. Bookends indicating, number one, whether we had low nitrogen cost and high wheat price. Low nitrogen price was 36 cents a pound. High wheat price was $7.50 a bushel, and we also threw in that $7 an acre application cost. In this situation, you can see that about 4 out of 10 times we had a profitable response. Now let's look at the other bookend. In this case, we're looking at high nitrogen cost, $1.02 a pound, low wheat price, $3.45 a bushel. And in this case, it took almost 8 bushel to the acre to pay for that 30 pounds of nitrogen. And you can see that for the most part, it took, we were only getting about 1 out of every 4 instances where we had a profitable return, and it fell off below the 15 parts per million. We actually had our 2 lowest categories, 0 to 5 and 6 to 10, that gave us about a 1 in 4 chance of having a profitable return. Now, both of those bookends are either above or below what the current wheat price and nitrogen prices are. So I've thrown in some numbers that indicate, given what prices are today, what the outcome should be. And in this situation, we're looking at best about 1 out of 5 to maybe 1 out of 3 opportunities for a profitable return. And it's because of this response that we're seeing with higher probability to the left of this bar right here that we again hung our hat on that 10 parts per million with a 6-inch soil sample as the indicator of a deficient situation and where you could benefit possibly from the use of fall nitrogen. All right, next question that we were trying to answer was just how deep do you have to sample? And I've talked about a 6-inch sample, and we actually divided our 2-foot samples into 3 increments. We had a 0 to 6, 6 to 12, and 12 to 24-inch samples. Now, there's 4 lines here, and what they're describing is the amount of residual nitrogen that we had in the fall for the various fertilizer treatments we had on the corn. And those treatments were 0, 120, 180, and 240 pounds to the acre. As you can see, even in the surface 6 inches, the amount of residual nitrate is pretty well bunched together. We're averaging that at about 14 pounds per acre. This was on a site, silt loam site, following a good corn crop. In other words, we utilized the majority of the nitrogen that we had given the corn that particular year. And there wasn't a lot of residual nitrogen remaining in the fall. Now let's look at an example where we had a drought year, had a very poor response to corn, or to the nitrogen we supplied the crop. Here we have our 4 different fertilizer treatments for corn with the 0 here and the high rate over here, the 240 pounds to the acre. Again, we measured the residual nitrogen after corn harvest. I'm just showing kind of the average for the 2 mid-level nitrogen treatments we had for corn, the 120 and the 180 pounds per acre. But you can see that we've got considerable amount of residual nitrate in the surface 6 inches, and as we go down through the profile, the amount declines, but it's considerably greater than it was for the 2008 year. Now, what you've seen here in these 2 charts, this pattern, with more residual nitrate in the surface and then declining as you move through the profile, was the pattern we saw time after time after time. And it's the reason why we settled on the 6-inch sample as being the appropriate depth to sample for determining residual nitrate in the fall. So based upon that, we came up with the recommendation, with our lab test recommendation, using the 6-inch sample, of if you have less than or equal to 10 parts per million nitrate, apply 30 pounds of N at planting. And if you're greater than 10 parts per million nitrate, no fall N can be applied per the regulation that we currently have. When we were working on this, it was developed as a recommendation, extension recommendation, and as you can see, what did happen is it did get turned into a regulation for the state. Now, the one criticism that occurred regarding the 6-inch sample is that it was 6-inch depth, and a standard soil sample is an 8-inch depth. And there's a lot of folks that like to take their fall samples, measure their pH, the amount of phosphorus, potassium they have in the soil, and make fertilizer adjustments at that point in time. So we've developed a recommendation based upon the 8-inch sample. Some of you maybe have seen this a couple times before. If you have, disregard what you saw before because we discovered a calculation error. What you see here today will be the correct numbers to use with an 8-inch sample, and that is if you have less than 8 parts per million nitrate in the 8-inch sample, you can use 30 pounds nitrogen at planting. If you're greater than that, no fall N can be applied. All right, there was also a desire to develop a quick test. The soil sample being sent to a lab sometimes means there's going to be some time before you get those results back. And as many of you know, planting in the fall, planting wheat in the fall frequently happens within just a few days after the corn is harvested. So there was a need to develop a quick test, and so we evaluated the Nitrate kits that are available in all the UME office. Of course, the Nitrate kits are the same ones that are used to conduct a PSNT, the pre-sidedress nitrate test for corn. The research that we conducted with the kit that we had in our lab proved to be very reliable. And in this chart here, along this axis, you have our latchet nitrate concentration. On this axis, we have the Nitrate kit concentrations, and you can see that they follow a almost a perfect line. We had an R squared of 0.98, which is nearly as good as you can get. However, we also realized that there was variability in kits, and more so probably in operators that are using those kits. So we did more testing to see how much the variability would be in these Nitrate kits. What we did is we used 20 of the samples, or about 20, it might have been 21 or 22, from that research that I've described to you earlier. We knew the nitrate concentrations in those samples. These samples had a range from 2 parts per million to as high as 64 parts per million nitrate. We split those samples among 10 nutrient management consultants and had them run them on their kits. What we found was that we were within plus or minus 2 parts per million 81% of the time in those comparisons that were run by the 10 nutrient management consultants on those 20 samples. Over 200 comparisons, and 81% of the time we were within plus or minus 2 parts per million. So based upon that, if you are using the quick test or the Nitrate kit for determining your fall nitrate level, and if you're using an 8-inch sample, I've got a couple of examples here. Of course, our critical nitrate level is less than or equal to 8 parts per million for using fall N if you have an 8-inch sample. And we have a reading of 9 parts per million. Now the variability is plus or minus 2 parts per million. You want to err on the side of caution, so you're going to subtract that 2 parts per million from the 9 that you've got. And you're going to have 7 parts per million, which indicates that 30 pounds of fall fertilizer nitrogen can be used per the regulation. Now I have another example for you. This one, we've got a Nitrate kit reading of 11 parts per million. The variability is 2 parts per million. We come up with 9 parts per million in this situation. And that means no fall fertilizer nitrogen can be used per regulation. All right, let's just summarize how you can utilize this residual N one more time. Now we've shown that there is a response to fall in by wheat as soil nitrate concentration in the surface 8 inches increases. The lower the nitrate concentration, the more likely you're going to have a response. Sites with less than or equal to 8 parts per million have a good probability of responding profitably to the use of fall nitrogen. But do keep in mind that this response will be variable. It's not a guarantee that if you have a soil nitrate content less than 8 parts per million, that you use fall nitrogen, that you will have a profitable response. All right. With that, the recommendations, if you are using a commercial lab, if you have a nitrate N concentration less than or equal to 8 parts per million, you can apply 30 pounds fall N or up to 30 pounds of fall N. If you want to use less, that's fine. And if your nitrate N concentration is greater than 8 parts per million, no fall N can be used per the regulation. Okay, the question is, if a soil test comes back greater than 8 parts per million, but the phosphorus levels are low and P is required, can we apply P? My take on the regulation is that there's no restriction on phosphorus. However, probably a lot of the phosphorus fertilizers out there also include some nitrogen. Maybe that if you're in that sort of a situation, you might have realized also that your P level was getting on the low level when you planted corn or your previous crop, and it might have been a better opportunity to try to adjust it at that point in time. Looks like we've got some others. MDA, P2O5 only, not if source brings in with it. Okay, well that answers that. And question, with the NitroCheck meter, we subtract 2 to evaluate whether N can be applied, correct? Yes, that errs on the side of caution. That's a maximum amount to subtract, and you want to definitely take advantage of the highest amount of variability. Question, that is on a 6-inch sample. No, that's on an 8-inch sample. That's using an 8-inch sample. If it's a 6-inch sample, you'd still use the same 2 parts per million subtraction. It is possible to apply only P2O5 without N. This is inconsistent with nutrient management regulation on beans. It is impossible to apply only P2O5 without N. This is inconsistent with nutrient management regulation on beans. I guess it is. Let's see, the MDA response there was, if it's impossible, then can't put N or P in the fall. And again, my recommendation would be is if you have a field where your phosphorus concentration, which declines very slowly, is getting close to that point where you need some, I think you probably want to address it with other crops and not particularly at that point in time. You're not going to see a dramatic change with perhaps one crop of corn in your phosphorus concentration. It just doesn't drop that quickly. Question, so a sample being pulled for a normal soil sample cannot be used or can be used to evaluate N application. It can be used, and that's the whole purpose behind the 8-inch sample recommendations. That's the standard soil sample depth, and that can be used, and that's why there were calculations made based upon an 8-inch sample. The research was conducted on a 6-inch sample. We realized after many folks at MDA told us that 8-inch was the standard sample that we need to make an adjustment. And that's why we've made an adjustment with recommendations for an 8-inch sample. Go ahead with the other component of this, and this is on spring nitrogen timing for the crop. And this becomes probably a more critical issue if you're not using any fall nitrogen. When should spring application occur? Well, of course, the UMA recommendation calls for top dressing at green up. We've already pointed out that there's a lot of questions about when is green up. And according to Maryland's commodity cover crop program, they will not allow any spring nitrogen prior to March 1, which is an indication that they're using that as the date of green up. So in theory, March 1 is not green up because years and locations differ for planting date and the accumulation of growing degrees. And we're going to talk a little bit about this temperature influence upon the performance of wheat and whether it actually has an influence upon what should be defined as green up for the crop. But first let's talk about when you plant wheat. And I'm sure many of you have probably seen a chart like this and are very aware that the recommendation is if you're planting wheat for commodity purposes, do not do so until the Hessian fly-free date has occurred for your region. Now that date can vary from where you're located in the state. I have my pointer here. If you're out in western Maryland, it can be as early as right at the end of September, 1st of October. If you're on the lower shore, that date falls more around the 10th or 11th of October. Now the optimum window for planting wheat is that period of about 10 to 14 days following this fly-free date. And what that means is if you plant during that period of time, you should have enough growth by the time you reach that point in the winter when you're going to go into dormancy, or semi-dormancy as we seem to do in this area in the last few years, to have about 3 tillers developed. And that's what your goal would be, is to develop 3 tillers. Let's talk a little bit about this response of wheat to temperature. And of course, wheat grows whenever the temperature is greater than 32 degrees. You can determine what growth stage your wheat is at any particular time by summing. Ooh, I lost my pointer. There we go. Oh, there it is. By summing the growing degree units that you have from the date you plant up until whatever particular date in the growth cycle you are currently at. Now the way you do that is you calculate the maximum temperature on any given day, add the minimum temperature that you have for that day, divide it by 2. In other words, you get the average, and subtract 32 degrees. 32 is the base temperature for this. And a mid-October day, growing degree units that would be accumulated would be 23, and this is based upon a high of 64 and a low of 46. You get into January, temperatures are a lot colder, have a high of 36, a low of 24, subtract off the 32 degrees from the average, and you get -2 growing degree units. However, that is not correct, and the reason that is not correct is because you actually have 0 growing degree units. And that's because you don't lose growth when temperature drops below 32 degrees. The wheat just stops growing. It doesn't grow backwards. This is a chart that Virginia Tech put out a few years ago, and it describes the response of wheat to the accumulation of those growing degree units. And you can see that it takes 235 of those units for the wheat to emerge. Tillering will begin when you've accumulated 775. And if you get to 1,200 units, you are at what's considered to be advanced tillering, or that's the number of units required to give you 3 tillers. And that's really where you kind of want to be at that point in time that we get the colder temperatures in winter. Now, jointing, according to this chart, starts at 1,350 units. Once jointing begins, tillering stops. So the goal would be to apply that first application of nitrogen sometime point in time you've accumulated 3 tillers and before joining begins. So is 1,200 growing degree units considered green up? And that's what the focus of a research project we've been conducting the last few years has been. The way we've been doing this project, and we started in 2000, 2010, 2011, we had only one site that year. Our second site was lost because of a very poor stand establishment. We've used 2 varieties, and that first year we had 2 planting dates. We've continued to look at the response to the use of fall nitrogen versus no fall nitrogen, but the important treatments in this study were the spring application dates. And we've used 4 different treatment dates. We've used March 1, which is MDA's date. We've used a date that's based upon the accumulation of approximately 1,200 GDUs. As you'll see, we didn't necessarily get the nitrogen out at exactly that point in time, but we tried to be semi-close to that time. Then we had dates of February 1 to 15, which is considered our early application date, and we had a late date, which occurs in mid-March. All right, let's look at what happened that first winter. And I do want to point out that that was a winter that was colder than our 30-year average. And you can see over here we've got 30-year average based upon an October 10th planting date of the accumulation of growing degree units for various stages of development along this axis right here. And in fact, 30-year average, and this was the Lower Shore, Poplar Hill location, 30-year average temperatures, we've accumulated enough growing degree units by the 6th of December to have 3 tillers. And in fact, it indicated that by January 1, we'd accumulated enough units for tillering to actually begin. Now, the year was much colder than average. Had 2 different planting dates for the wheat, October 13, October 27. We didn't accumulate 1,200 GDUs until the 12th of February for the early plant date, and it was not until the 12th of March for the late plant date. And of course, using the 1,350 GDUs, it took until mid-March for the 1,350 GDUs to be accumulated, or after April 1 for the late plant date. What kind of response did we see? Well, I'm showing you the yield response for 3 different application dates, 8th of February, 3rd of March, 14th of March. And the reason we only have 3 application dates is because for the early plant date, our February 8th application date was actually the same as the date that we accumulated our 1,200 growing degree units. Then we had our March 1 date, or as close to it as possible. It was actually March 3rd. And then we had our late date, March 14th. Our best yield was attained when the applications went out prior to March 1, or close to March 1. For the late planting date, October 27th, and in this case, it was this red bar here that we actually accumulated our 1,200 GDUs, and that was then the same date as our late application date, so those 2 dates are combined. But again, what we saw as far as yield response was best yield was attained if we got our nitrogen applied either in early February or prior to about March 3rd. Okay, so that seemed to fit the premise that maybe March 1 wasn't the best date, maybe a little bit earlier would possibly work. So we repeated this study in 2011, 2012. During the second year, the only difference was we actually had 5 sites that we got planted that particular year. We used the same treatment dates for spring N application. Let's just look at growth based upon the accumulation of growing degree units for each of the 5 locations for that particular year. Here's the planting dates that we used in October 11, and then we had an October 26 at Poplar Hill, October 18 at Y, November 6 at Beltsville, a late date, and October 10 at Keedysville. That was a warmer winter than usual. We actually accumulated our 1,200 growing degree units at 4 of the 5 locations by the end of December in that year. And in fact, if we were using 1,350 units for initiation of joining, we'd also accumulated those by the end of January at all locations but our late planting date. Well, this was causing some concern because there was no joining going on at those dates. All right. So I went back and started evaluating the various requirements for reproductive growth. Of course, we grow winter wheat, so it requires vernalization. I'll talk a little bit more about vernalization in a second. And the other thing was the accumulation of 1,350 GDUs for joining, and obviously that wasn't happening. So question was vernalization later because 2011-12 was a very warm winter? All right, well, what's necessary to vernalize wheat? And vernalization is important because it is what actually, you have to have this cold period in order to initiate the reproductive growth in wheat. Vernalization will occur when temperatures are less than or equal to 42 degrees. And I use the average daily temperature. If it's below 42 degrees on any particular day, the average temperature for the day, I call that a vernalization day. Most of the varieties we produce in this region require 30 to 40 days of cold exposure. And what happens after the vernalization is complete is that the spike primordia will form. And if you would dissect wheat, get down to the growing point after you've accumulated enough vernalization days, you would actually see the formation of the tiny head or the spike. If you had a microscope, you could see the head and the formation of the kernels on that spike. So it's at that point in time that your head size and kernel number is determined. So let's go back to that growth chart that we had, and let's throw in that vernalization requirement, see if we had attained it and when we attained it. And at all of the locations, we had had enough vernalization, even with the warmer winter, by February 10th at the latest. So I was still scratching my head because there was no joining. So we've ruled out vernalization. It seems like this accumulation of 1,350 GDUs for joining isn't the answer. What else could possibly be going on? And what I discovered with some literature review and work that was done by USDA scientist Betty Klepper and her team, both at Nebraska, and then she later moved on to Oregon, was that there was a day length factor involved. In other words, a photoperiod response was necessary. And what Betty Klepper's team determined was that you need the accumulation of about 700 GDUs after our day length starts getting longer, which means after the winter solstice, or she uses January 1 as sort of an easy date for this. That if you get those 700 GDUs, you will have the initiation of joining. Okay, let's add that to our growth chart for 2011, 2012, and that accumulation of 700 GDUs occurred about mid-March. Now, of course, that means it's time for the second application of nitrogen. So for that green up application of nitrogen, it should be sometime between the accumulation of 1,200 GDUs or formation of 3 tillers and prior to when joining is going to be initiated, and probably after you've gotten this vernalization requirement fulfilled, which indicates that that first nitrogen application in 2011-2012 would probably have performed the best if it was applied probably sometime in January or during February, or at least before that March 1 or at that March 1 date. So I was happy. We were able to at least have joining at this point in time. So things were starting to fit again. All right, so what did we see as far as yield response in 2011-2012? Again, we've got our 5 locations going down the left side of the chart. I seem to have lost my pointer again. Let's see if we can get it back. There it is. All right, let's just look at what happened at each of these locations. All right, at Poplar Hill, the early plant date, we saw our best response with applications that occurred March 1 or with the later application. The numbers The dates you see in parentheses here were the actual dates of fertilizer application. Okay? So for early planted wheat at Poplar Hill, March 1 or later was our best response. For the later planted wheat at Poplar Hill, it didn't matter when the spring nitrogen, the green up nitrogen went on. Performance was the same. At Y, didn't get the spring nitrogen until the 24th of March, or the last application, the late application, and that proved to be the best. Better than the earlier applications that we had. Beltsville, our late planted wheat, again responded to a late application of spring nitrogen. Keedysville was the only location that responded to the spring nitrogen application based upon 1200 GDU accumulation. So, this is me. I'm still scratching my head, because after two very opposite fall-winter growing seasons, the use of a GDU method for determining the first date of spring end has produced very different results. With the colder winter that we had in 2010, 2011, an application March 1 or earlier was favored. With the warmer winter, the winter you would have assumed getting nitrogen out earlier would have performed better. We actually saw our best response at 4 of the 5 locations with an application either March 1 or later, rather than the earlier application. And this, at this point in time, kind of indicates that MDA's March 1 application date appears rather practical. Now, we are continuing to test. We've got 4 locations this year. We plan to put the study out again starting in the fall of 2013, so we'll get additional information then. And I just want to kind of close with Paul Harvey's old saying of stay tuned for the rest of the story. And with that, I thank you for your attention. It looks like I have finished within my time limit, and I guess we probably have some time for a few more questions.
Question, Dr.
Paul's question was the response that we saw, and I guess it's in reference to the second year, was in response to the nitrogen, or the rainfall that we had following near the green up application. It was a really dry winter last year, and I don't think the amount of precipitation we received had any impact on it. Okay, there's a question. Last year in your later N applications, was that the first of a split application or all the N applied in one? That was the first of a split application. Yeah, the second application at all those sites went on probably early April at the very latest. Okay, if we needed N in the fall but chose not to apply N in the fall, would this change the spring N need? No. The interesting thing, and what I showed you in those results for the response to spring N application was the average over fall N and no fall N applications, because there were no significant differences between performance, no interactions based upon spring application timing with fall N use. I mean, it's pretty cut and dried as far as if you put fall N out and then come with the spring N application, or if you don't use any fall N and come with the spring application, the timing is the same. Are you looking at usage of time-release nitrogen fertilizers on spring wheat applications using only one application rather than 2 split applications? No, I'm not. That does sound like a very good project. Should be investigated, but I'm not doing it currently.
And predict some of that you risk.
Okay, go ahead, Josh. Josh is here. He's got an answer to that from some work that was done.
Delaware did some work on this. I don't have all the details, but with a slow release nitrogen, actually because of the cool weather and something like a polymer coated urea like ESN is moderated or mediated by diffusion through that polymer coating. And that's a temperature dependent rate, And so they actually saw N deficiency because it was too cool for consistent release of the nitrogen through the polymer coating. So that would be a concern as far as conserving that nitrogen.
Question, are you comfortable with a single N application, and if yes, at what stage or time frame in the spring? I still like to see split applications. However, if it appears that a March 1 or later date is functional, perhaps one application will be okay. The problem with that is the potential for loss. If we happen to have a very wet spring with one application, you just stand, you have an opportunity for greater loss than if you have the split application.